Hi everyone. Today's topic is computation of smallest eigenvalue and the corresponding eigenvector of a square matrix by inverse power method. So we have already learned power method to find the largest eigenvalue. Here we are going to follow the same procedure except that in place of A we are going to use A inverse. So in the working procedure, first we have to find A inverse using the formula 1 by determinant A adjoint A. And after evaluating A inverse, we should form the product A inverse x naught. And after solving A inverse x naught, write the solution in the form of lambda 1 inverse x1. So as usual, we are going to choose the initial eigenvector x naught, which is a column matrix, and proceed to find A inverse x naught equal to lambda 1 inverse x1. Which gives us the first approximation. Now going ahead with the second approximation, we would form A inverse x1 equal to lambda 2 x2. A inverse x1 equal to lambda 2 inverse x2. Now repeat the iterative process till a desired accuracy of lambda inverse and x is obtained. Lambda inverse is written as 1 by lambda, and lambda will give us the smallest eigenvalue and x will be the corresponding eigenvector. So let us take a 2 by 2 matrix as an example to find the smallest eigenvalue. So find the smallest eigenvalue and the corresponding eigenvector of the matrix A equal to matrix 4, 2, 1, 3. So first we have to find A inverse using A inverse equal to 1 by determinant A adjoint A. So determinant A is found to be 10. Adjoint A is matrix 3 minus 2 minus 1, 4. Hence A inverse is 1 by 10 into adjoint A, that is matrix 3 minus 2 minus 1, 4. Evaluate and we will get 3 by 10 minus 2 by 10 minus 1 by 10, 4 by 10, which gives us the decimal 0.3 minus 0.2 minus 0.1, 0.4. So this is A inverse matrix. Having found the A inverse matrix, choose the initial eigenvector x naught as 1, 0. Form A inverse equal into x naught, that is 0.3 minus 0.2 minus 0.1, 0.4 into matrix 1, 0. The product matrix will give us 0.3 minus 0.1. Like in largest eigenvalue problems, we retained this value 1 throughout the problem. So even here, as in the x naught initial eigenvector, so even here throughout the problem we are going to retain 1. Hence take 0.3 common, that is divide by 0.3, that will give us 0.3 into 1 minus 0.33. Hence 0.3 gives us lambda 1 inverse and the matrix, column matrix is x1. Thus A inverse x naught is expressed in the form of lambda 1 inverse x1, where x1 is 1 minus 0.33. Repeat the iterative process by finding the second approximation. Hence we will find A inverse x1 equal to 0.3 minus 0.2 minus 0.1, 0.4 into matrix 1 minus 0.33. That will give us 0.366 minus 0.232 and write it in the form of 0.366 into, so divide these terms by 0.366. That will give us matrix 1 minus 0.634. That leads to lambda 2 inverse x2. This way we are going to repeat the process till we reach a desired accuracy. Hence A inverse x2 is formed and that gives us 0.427 into 1 minus 0.829. That leads to lambda 3 inverse x3. So there is a variation between lambda 2 inverse and lambda 3 inverse. Hence we are going to repeat the process. Thus A inverse x3 is formed and that leads to 0.465 into matrix 1 minus 0.927 that gives us lambda 4 inverse x4. So hence we can see that here 0.4 is repeated, at least 2 decimal parts shall repeat. Therefore we proceed with the next iterative process. A inverse x4 is formed, that gives us 0.485 into matrix 1 minus 0.971, that is lambda 5 inverse x5. Like this we proceed to find A inverse x5, that gives us lambda 6 inverse x6. So we see that lambda 5 inverse is 0.485, lambda 6 inverse is 0.494. So the values are getting much closer, hence we proceed to find the next iterative value, that is A inverse x6, that gives us 0.3 minus 0.2 minus 0.1 0.4 into the x6 matrix, that leads to 0.497 into matrix 1 minus 0.993, that gives us lambda 7 inverse x7. So what we have observed is all the lambda inverse values are 0.46 from lambda 4 inverse. If we see, we have 0.46, 0.48, 0.49 and again 0.49 has repeated, which means that the values are approaching 0.5. 0.5 can be written as 1 by 2. So lambda inverse is 1 by 2. Hence lambda is 2. Thus the smallest eigenvalue is 2 and the corresponding eigenvector is matrix 1 minus 0.993 transpose. Now let us go on with a 3 by 3 matrix to find the smallest eigenvalue and the corresponding eigenvector of A equal to 3, 0, 1, 0 minus 3, 0, 1, 0, 3. Let us do only 4 steps. Now first we have to find A inverse with A inverse equal to 1 by determinant A adjoint A.